Lesson 44, half-life. And if you've done math 30-1, you should have a pretty good indication of half-life and how it works mathematically. Because we do it in physics almost exactly the way that you do it in math. A half-life of an element is the time it will take for half of the parent atoms to transmutate into something else through alpha or beta decays. And then you'll see the extraordinary range of decay times. We have from 10 to the negative 22 seconds to 10 to the 28 seconds, which is 10 to the 21 years. Just as I believe uranium, some forms of uranium have half-lives of about 4 billion years. So in other words, if I have 10 kilograms of uranium right now in my hand, in 4 billion years from now, it will be 5 kilograms of uranium, and the rest of it will have transmutated into something else. And his half-life is really fascinating because of the whole concept of carbon dating. The half-life of carbon-14 is 5,730 years. So again, if you got 10 kilograms of carbon-14, 5,730 years from now, you'll have half of that. In another 5,730 years, you'll have half of that. So then you only have 2.5. Actually, let's write that down. So if you start off with, if I'm going my time here, time 0, and here's my mass, about 10 kilograms, and 5,000, I'll have 5 kilograms. If I double that, it will be 11,460. I will have 2.5 kilograms. And then I add another 5,700, it will be 1.25 kilograms. And then 0.753, something like that. Anyway, you get the idea. So every time a half-life occurs, you have half the amount of the substance. Therefore, you will know that it's an exponential. It's exponential graph, not a linear graph. All right, and you can read over all this. Oh, okay, there we go. That's what I was just talking about right there. Okay. Activity. The activity is usually measured in becquerels, and the activity of a substance, it measures the number of nuclei that decay per second. This is, for example, if something has 72 becquerels, then it decays 72 nuclei decay per second. And this is what's important in this lesson, in addition to the math, which we're going to go over in a minute. The other important thing is these graphs. So this is a percentage versus half-life graph, and they can ask you how much of the material remain after 2 half-lives, and you would just say, oh, after 2 half-lives, looks like around 25% of the material remains. Right? Now that makes sense, doesn't it? Because if after 1 half-life, it's obviously going to be 50. After 2 half-lives, it's going to be 25. After 3 half-lives, it's going to be 12.5, and so on and so on. Okay, now let's go into the math. And here's the formula that we use in physics. N, which means the final amount, equals the initial amount times the half-life times to the exponent n. You're going to see this formula in many different forms. In math, you may have seen it as, some people use A equals A naught half-life to the exponent T over D, where T is the amount of time and D is the amount of time for the half-life to occur. So this is kind of the one that's a little easier to memorize. Let's do this example. Example number 2. Marie Curie had 765 grams of polonium, which has a half-life of 138 days. After 3.8 years of refining uranium, she goes to the box to get her polonium, determine how much polonium there is in the box. So the initial amount, which is going to be your N naught, equals, 765 grams. We are trying to find out what the final amount is. And we have the half-life, which in this formula that I've written up here, that is the time for one half-life. And then here is the time period that we're referring to. So in that case, that would be the 3.8 years. So we're gonna have to convert one to the other. Let's go with, so we're gonna say that the D value in this case is 138 days, and we're gonna say that the T value of this is 3.8 years. So it's just gonna be 3.8 times 365, which equals 1,387 days. So 3.8 years is 1,387 days. The substance has a half-life of 138 days, and we can just plug them now into that formula in one step and get the answer. Which turns out to be, so 675 times 0.5 to the exponent by 138. Okay, I plugged that into my calculator wrong, times 0.5 to the exponent, 1 divided by, and you should get an answer of 0.72 grams. All right, pretty straightforward. Example number 3, you have 75 grams of lead. It has a half-life of 10.5 hours. Determine how long it will take until only 9.3 grams remains. Now, just so you know, all the questions in Physics 30 are designed to, they all have easy numbers. So you can actually just guess and check these answers. Okay, actually, let me backtrack a little and outline why that is. You have 75 kilograms of lead. The half-life, the D value, is 10.6 hours. Determine how long it would take so that the final amount, sorry, this is N naught, so that the final amount is 9.3. 9.3 grams. Okay, so that looks pretty straightforward. We set it up as in oops. So we set it up like that, and then we're solving for t. Well, if you've taken Math 30-1, then you will know how to solve for t using logarithms, right? You're going to divide both sides by 75, and then you're going to take the logarithm of both sides and the t. Actually, let's just do that quickly. So you're going to divide by 75. What does that give you? It gives you 9.3 divided by 75 is 0.1. And then you're going to say to solve for the variable t, since this is part of the exponent, I'm going to take the log of both sides. So I'm going to get log this equals, and then I'm going to use my logarithm laws, and the exponent jumps out in front, t over 10.6 times log 1/2. And from there on, it's easy to solve. It's just log 0.124 divided by, or end of brackets, divided by log 0.5 equals times 10.6, and I get the answer 31.9. hours. Okay, so if you've taken math, you can solve it that way. However, just so you know, in Physics 30, the questions are designed that you can solve them without knowing logarithms, just in case you took physics in the first semester and didn't take math 30-1 until the second semester. And so you can solve this one by simply, crude but effective, by guessing and checking the answer. So you can just do it manually. What you can say is, okay, well, if I started with 75, so here's my time, here's my amount. At time 0, I have 75. After 1 half-life, after 10.6 hours, I'm going to have 37.5. After 2 half-lives, which is going to be 21.2, I'm going to have half of that, which is 18.75. And you can see I'm trying to get to this. I'm trying to get to 9.3, so I'm getting pretty close. And after another half-life, which is now going to be 31.8, I'm going to have that divided by 3, which is 9, that divided by 2, half of that, 9.375. So you can see I can get my answer like in a fraction of the time by just kind of guessing and checking. Now, do I get an exact answer here? I got 31.8. The actual answer is exactly 31.9. So I didn't get the best answer because it's a little high, as you can see. But in Physics 30, the questions are designed that you could just guess and check the answer. And more often than not, it would take you less time to do it than the logarithm. Just doing the logarithm is just way more intellectually, emotionally, and spiritually satisfying. So if you know how to use a logarithm, do it. Okay, we're moving on to fission and fusion for lesson 45. We'll see you there.